Okay, so I will describe some recent work that on slow quantum quenches, and this work is done with Lakshita Jindal. She's somewhere here, and she's a PhD student finishing her PhD with me. And this work should be out online in a few days. Okay, so so this work is on slow quenches. So let me start by saying what is a slow quench. So what we are doing is we're thinking of a classical or quantum system which has a second order phase transition in its stationary / ground state. And what we do is we're asking, suppose we prepare a system in a disordered phase and it's quenched to, let's say, ordered phase, but in a finite time tau. So what you're used to is typically thinking of instantaneous quenches. This is a finite time quench. And then one is interested in asking questions about the dynamics during the quench process and at the end of the quench process. So let me give you a couple of specific concrete models here. So here, this is some material which has a phase transition between paramagnetic and ferromagnetic phase. The system is prepared at very high temperatures and then it's cooled down at below Tc. So suppose you take this time tau to be very small. So you basically have instantaneous quench, and then you look at the end of the quench, then your state would be same as what you started with. On the other hand, if you do this process very, very slowly, sufficiently slowly, then you will reach equilibrium state or somewhere near to it. We are interested in this regime where this time tau is neither too small nor too large. Okay, so this is the focus of work. Okay, let me give one more example. Here I'm showing you the simulation results of the one-day Ising chain using Kawasaki dynamics. Again, we prepared system at large high temperatures and quenched it using some protocol to 0 temperature. And what we just did is to measure the mean number of domain walls in the system. So what's shown here as a function of time is the number of domain walls in excess of what you would expect had the system been in equilibrium. So this is the excess or residual defect density shown as a function of time. So what you see here is that at short times, when the system is far from the critical point, it's able to relax as I perturb the temperatures. Temperatures perturb, temperatures change, and therefore the system is able to relax to it, and therefore it's nearly equilibrated. So therefore this excess defect density is very, very small. Look at the Y scale, the numbers, okay? But at some point, as you get closer and closer to the 0 temperature, to the critical point, this excess defect density increases. And it's higher if the the time tau is small. So there is some time scale below which adiabatic evolution is good, above which it breaks down. And we would like to understand what this time scale is. So therefore, I will think in terms of quantum phase transition. So the idea is, suppose I have a quantum phase transition by varying a temperature, according to some parameter G is varied in time tau. There are 2 time scales in this problem. One is that relaxation time. As I already said, you perturb a parameter G, and the system can relax. But the other time scale is the inverse rate of change of the energy. If the relaxation occurs sufficiently slowly, then in that case, you have this relaxation time is smaller, then you have here adiabatic evolution. But at some point, these 2 time scales will become same order, and finally, relaxation time will be very, very long, and then you'll enter the state. And the assumption in this Kibozelic argument is that now the system is frozen at the state when it entered this region. Okay? And then again, relaxation time decreases, and then again, adiabatic evolution resumes. So the key idea here is that you can find out this time scale, this Kibozelic time scale, when these 2 time scales, the relaxation time and the inverse rate of change of energy, they are the same order, and associated with that is a length scale also. Okay, so this is this theory about this excess defect density, this KZ length scale. The physical meaning of this is the excess defect density. That means you can think of it as the typical distance between 2 kinks. And this has been, this defect density typically decreases as a power law in the quench time. And the scaling has been verified in numerous ways, and it's a very, very well established scaling relations. But however, this picture of picture of KZ, it does not provide us an understanding of full dynamics, because we're thinking that in between somewhere there's a frozen dynamics. And today I'm interested in correlation functions. Correlation functions, it turns out also it does not capture. So the idea here is, it turns out that correlation functions, certain correlation functions, they're not fully described by just the KZ length scale. Secondly, you expect that because we're thinking of adiabatic stuff on the either side of this frozen regime, it may decay exponentially. That's also not true. So this is the key take-home message, and I will now elaborate on this point. So like Manmeet said, I am thinking of again transverse field as a model in one dimension, however, and this is the interaction term, and this is the transverse field, which is time dependent. And as she already said, there's a quantification at g equal to 1. So there's a bunch of transformations that you have to do to deal with this, and it turns out the quantities of interest that reduces finally to a two-level problem. So that's very nice and easy and very good. However, you see, this is not always exactly doable simply because you wind up with a second-order differential equation with time-dependent coefficients. And this can be solved only in a very specific case. In this case, it turns out it's exactly solvable only for linear quenches. Today, I'm interested in Kink-Kink correlator. It's a 4-point function, but it turns out you can do something simple here. This is in a longitudinal direction. This Kink-Kink correlator, it has two parts. There is a term which, if I write down for this two-level system, if I write down the density matrix, then this k on is related, depends upon the diagonal elements, and then there's a part which depends on the off-diagonal elements. So for the linear quenches, what is known is that this on-diagonal part depends on the kz scale, which is expected. However, what is unexpected is that this scaling function is a Gaussian. The off-diagonal part is also Gaussian, but there's an additional length scale which goes like root tau log tau. It is additional log tau here. And we are interested in asking what happens with the other quenches. Are these results universal? So we took a quench which is, goes as a power law in the vicinity of the critical point. This is not exactly solvable, but we tried various things. And I will just, one of the methods was simply the adiabatic perturbation theory, the idea being that because quench is slow, so you're close to the eigenbasis of the instantaneous Hamiltonian. And you can expand your state vector as a linear combination of that. You wind up with this kind of integrals, which is using the standard saddle point methods you can solve. And I'll just give you the answers now. So for the diagonal correlator, this is what we find. Scaling function, like the linear quench, depends only on one scale, namely the kz length scale. Like linear quench, the scaling function is non-exponential. In particular, we can show that for sublinear quenches, it decays like this kind of compressed exponential with the exponent here 1 plus omega. It's changing continuously with the quench exponent. For superlinear quenches, the tail part has the same behavior, but at short distances, it's a Gaussian. For the off-diagonal correlator, there is an additional length scale, the new length scale, which is non-kz, for sublinear and linear quenches. For superlinear quenches, you can describe the whole thing with just a kz length scale. And I forgot to mention this here. This origin of this new scale lies actually in the so-called frozen regime. So we assume that the frozen regime, there are no dynamics. Actually, there are non-trivial dynamics which are giving rise to this new scale also. So I'm almost done. So basic point is simply this. Non-linear quenches, hardly anything is known. Only thing that we know is basically up to something like a 1-point function. So here we have given new results for the correlators, but this is a specific correlator that we tackled. But there are other correlation functions which are interesting as nothing has been done, but this is harder to calculate, perhaps interesting also. And there's some obvious directions. For example, this is an integrable chain, and we expect it'll go to GE at large times. Is there any signature of the quench protocol? Can it carry? I don't know, but it might be interesting to look at. Manmeet already spoke about equipity. That also has been done for linear quenches. What happens if there's a non-linear quench? So thank you, and sorry for taking more time. Thank you very much.